In this module, you will learn about the mathematical formulation relating to work done by a variable force and the concept of potential energy. We know that the work done by a force F on a body is W is equal to Fd cos theta, where d is the displacement of the body and theta is the angle between the force and displacement. But in practical situations, a body may be acted upon by a force which may not be constant and is a variable force. A variable force is a force whose magnitude or direction or both vary during the displacement of a body on which it acts. Let's look at an example of a variable force. As the spring oscillates between the extreme positions O and A, the restoring force on it keeps changing with the displacement from the mean position. This is a variable force on the spring. How do we calculate the work done by such variable forces? Let us suppose that a body moves along the direction of a variable force acting on it. We then plot a graph of force F versus displacement x, which helps calculate the varying force with the displacement. The work done by the variable force can be found by calculating the area under the graph. To find the work done by this variable force, we divide the total displacements into n number of small elements or segments: delta x1, delta x2, delta x3, and so on till delta xn. The work done with respect to the first segment, delta x1, is the area of this first segment, that is, F1 into delta x1. Work done with respect to the second segment, delta x2, is the area of the second segment, that is, F2 into delta x2. For the third segment, delta x3, work done is the area of the third segment, that is, F3 into delta x3, and so on. Here, we assume that the force remains constant for each small segment. Thus, the area of any segment will be denoted by the expression delta A is equal to Fx delta x. Let this be equation 1. The total work done is equal to the sum of the areas of all the small elements, which is equal to the summation of F delta x taken within the limits from x1 to xn, as in expression 1. If the size of each segment is very small, each segment tends to 0, and we have a large number of such segments. And the total work done is calculated as W is equal to sigma of F delta x between the limits x1 to xn, as the limit of x tends to 0. Let this be equation 2. Hence, the work done for a varying force can be expressed in integral form, as W is equal to integral f dx in the limits x1 to xn. Let this be equation 3. We know that according to the work-energy theorem, the work done, W, by a net force on a body is equal to a change in its kinetic energy, Ke, as in expression 4. W is equal to delta Ke. Let us now try to prove the work-energy theorem for a variable force. We know that the work done by a variable force can be found by the expression W is equal to integral f dx in the limits x1 to xn. Let's call this equation 5. If the velocity of the object at an instant is v, then its kinetic energy at the instant is expressed as half mv square. Let this be equation 6. On differentiating equation 6 with respect to time t, we get the rate of change of kinetic energy as dk by dt is equal to d by dt of half mv square. Thus, on simplification, we get dk by dt is equal to half m d by dt of v square. On further simplifying, we get dk by dt is equal to half m into 2v dv by dt. Thus, dk by dt is equal to mv dv by dt. This can also be written as dk by dt is equal to mdv by dt into v. On the right side of the equation, we know that dv by dt is the rate of change of velocity, which is the acceleration of the body. Thus, we get dk by dt is equal to mav. However, according to Newton's second law, F is equal to ma. Therefore, we get dk by dt is equal to Fv. Also, the velocity term v in the expression can be represented as the rate of displacement v is equal to dx by dt. Hence, we get expression 7 as shown, which is dk is equal to f dx. Integrating expression 7 in the limits from x1 to xn for the displacement and for k1 to kn for the corresponding kinetic energy, we get integral dk within the limits k1 to kn equal to integral f dx within the limits x1 to xn. The left side of the equation indicates the change in kinetic energy, and the right side of the equation indicates the work done on the body by the variable force. Thus, we see that the work done by a variable force on a body is equal to the change in kinetic energy of the body. This proves that the work energy theorem holds true for a variable force. Now let us learn about potential energy. The energy stored in a body by virtue of its position or configuration is called potential energy. Consider a body of mass m placed on the surface of the earth. The weight of the body placed on the surface of the earth is denoted by mg. Let this be equation 9. To raise the body through height h above the surface, the minimum force required is its weight, which is equal to mg. Consider the upward direction to be positive. The work W done to raise the body through height h against the gravitational force of attraction by an external force is mgh. Let this be equation 10. This work is stored in the body as its potential energy. The gravitational potential energy of the body as a function of height h is denoted by V of h, and it is the negative of work done by the gravitational force while raising the body through the height. Thus, we have V of h is equal to mgh. If h is the variable, it can be easily shown that the gravitational force F is equal to the negative of the derivative of V of h with respect to h. Thus, F is equal to minus d by dh of VH equal to minus d by dh of mgh, which is equal to minus mg. Let this be equation 11. The negative sign indicates that the gravitational force is directed downwards. Hence, when released, the body comes down with increasing speed, converting its potential energy into kinetic energy. The body strikes the ground with the velocity v, denoted by the expression v square is equal to 2gh. On multiplying both sides of the above equation with half m, we get half mv square is equal to half m into 2gh, which is equal to mgh. The left side of the equation is the kinetic energy of the body on reaching the ground, and the expression on the right is the potential energy stored. Thus, this proves that the potential energy of the body is transformed into its kinetic energy when the ball is released. Hence, physically the concept of potential energy is applicable to the type of forces where work done against the force is stored in it. Mathematically, the potential energy V of x is defined for any force f of x, which can be written as f of x is equal to minus dv by dx, shown by expression 12. Integrating on both sides of the expression within the limits of initial position xi and final position xf. And on simplifying, we get minus of Vf minus Vi. On further simplification, we can arrive at the conclusion as shown in equation 13. Integral of fx dx within the limits xi and xf is equal to Vi minus Vf. From equation 13, we can see that the work done on a body by the force depends on the initial and final positions only, and not on the path followed by the body. Such a force is called a conservative force. By definition, if the work done by a force is independent of the path followed, then it is a conservative force. Such a force is characterized by equation 13. Gravitational force and elastic force, in the case of a stretched spring, etc., are examples of conservative forces. Let's try to understand these forces. We see that when a box is dropped from a certain height, the work done by gravity on the box is mgh. When the same box slides down the smooth inclined plane at an inclination of theta with the horizontal, the force acting down along the incline is mg sin theta. The distance travelled by the box is L. And hence, the work done by gravity on it is denoted by the expression W is equal to mg sin theta into L. On simplifying, we get work done as mgh as shown in expression 15. So far, we have studied conservative forces. Let us now learn about non-conservative forces. If the work done by a force depends on the path followed, it is a non-conservative force. For example, friction is a non-conservative force. Consider a box placed on a rough surface and moved through different positions A and B in different paths. In the first case, the box is moved along a straight path from A to B as shown. In the second case, the box is moved along a zigzag path from A to B as shown. The distance travelled is different in both cases. Hence, the work done to overcome the friction in both cases is different and is dependent on the path followed. Thus, friction is a non-conservative force. You have now reached the end of this module. In this module, you learnt that a variable force is a force whose magnitude or direction, or both, vary during the displacement of a body on which it acts. The work done by a variable force can be expressed in integral form as W is equal to integral f dx within the limit x1 to xn. The expression W is equal to integral f dx within the limit x1 to xn proves the work-energy theorem for a variable force. The energy stored in a body by virtue of its position or configuration is called potential energy. Mathematically, the potential energy V of x is defined for any force f of x, which can be written as Fx is equal to minus dV by dx. If the work done by a force is independent of the path followed, then it is a conservative force. If the work done by a force depends on the path followed, then it is a non-conservative force.